All semester long, we've said the answer to the question, what is a force, is that a force is an interaction between two objects. It's how one object pushes or pulls on another. And it's easy to see how objects do that when they're in contact with each other. But what about these forces? These forces we labeled as non-contact forces, and we said that for the gravitational force, the electric force, the magnetic force, our objects that are interacting aren't in contact. So this begs the question, how do two objects push or pull on each other if they're not in contact? The idea that we're going to start to lay out in this video is that they interact through fields. So the gravitational field is the way that two objects are going to interact with each other via the gravitational force. The same thing's true, as you'll see in the second semester, when you talk about the electric force and the magnetic force. There's an electric field and a magnetic field that objects will use to interact with each other through the electric and magnetic force. The idea of a field is a pretty abstract concept. And so we want to start by thinking about fields using the field you know best, which is the gravitational field. Now, the other thing that we've talked about all semester long is that the gravitational force near the Earth's surface is a force that points downward, and you can calculate the magnitude of that force by taking the mass of whatever object that force is exerted on and multiplying it by little g, the gravitational acceleration, 9.8 meters per second squared near the surface of the Earth. But part of what we want to do is come back and emphasize that we've undersold the importance of this equation. What this equation is really doing is it's telling us how the gravitational force relates to the gravitational field. So little g is really the gravitational field. We tend to call it the gravitational acceleration because that's what its units are. But it's really the gravitational field. And so when we think about this equation that says the gravitational force acting on your object is equal to the mass of the object times the gravitational field, this tells us a couple things. One, it says that the gravitational force and the gravitational field always point in the same direction because this mass is always going to be a positive quantity. The other thing it says is that you calculate the gravitational force on your test mass. So the T here is because we're describing this mass as a test mass. And we'll see where that label comes from in a minute. But if you're interested in calculating the magnitude of the gravitational force on this test mass, then the two things that you want to multiply together is whatever the test mass is, that value, times the strength of the gravitational field at the point where your test mass is placed. So what this means is that the gravitational force is still an interaction between two masses. There's a source mass. The source mass creates a gravitational field. That gives us little g. The test mass is then placed at a point in that gravitational field. So our two masses have been sitting here all along in this equation. One of them, the test mass, is explicitly out front. The source mass is hidden inside this gravitational field value. So if we want to think about the gravitational field near the Earth's surface, what we know is it points downward, it is constant in magnitude, and it has a value of 9.8 meters per second squared. So we've referred to this as the gravitational acceleration, but this is really telling us about the strength of the gravitational field. So if I take some mass and place it in the gravitational field, there's going to be a gravitational force that acts on that mass. So fundamentally, where does that force come from? Well, the Earth creates a gravitational field. When you place your test mass in the gravitational field, it is now attracted to the Earth through the gravitational force because we now have a way to relate that gravitational force to the gravitational field. Here's that relation. So we know the gravitational force now points downwards because the gravitational force and the gravitational field are going to point in the same direction. And the magnitude of the gravitational force says, well, whatever your test mass is, multiply that times the magnitude of the gravitational field, which in the case of the Earth is 9.8 meters per second squared. So let's consider two massive particles. The particle on the left, particle on the right. And again, I know that they're each going to feel a gravitational force, so they're going to be gravitationally attracted towards each other. So if I want to think about where this gravitational force acting on the particle on the right comes from, the idea here is that the particle on the left is creating a gravitational field. Point P is the point where that other particle was located. And so I can think about the gravitational field at point P, so that now when I come back and place my second particle there, if I know what's going on with the gravitational field, that's going to tell me what's going on with the gravitational force. Because of course I can relate these two quantities through this equation. So my second mass gets placed in the gravitational field and is attracted to the first mass by a gravitational force. My second mass senses the presence of the other by the fact that when you place it here, it sees the gravitational field and reacts to it via the gravitational force. But of course we said that my first particle, the one on the left, also felt a gravitational force. Where is that coming from? Because this second particle, when you bring it up and put it at point P, it also creates a gravitational field in the space around it. The gravitational interaction between these two particles, how they're attracted to each other, is because each of them is creating a field that the other is responding to. And so fundamentally, what that gravitational field describes is how mass influences the space around it. As you can see, just from looking at these vectors, as your particle gets closer, that gravitational field gets stronger. As it moves farther away, that gravitational field gets weaker. So the field describes how a massive particle influences the space around it, and then F equals mg tells us how that influence on the space is going to be felt by another mass that you place at a point in the space around your first particle. So that's the big idea in terms of what's going on with fields. So let's think about problems that we've been working. And so again, when we talked about the gravitational force, we worked through an example problem where we said we're interested in calculating the net gravitational force exerted on particle 1 by the other two particles. So in terms of thinking about the gravitational field, this gives us a way to reframe this problem. And what it says is, masses 2 and 3 here are your source masses. They're going to create a gravitational field at the point where you've placed your test mass. So mass 1 in this case, because it's the one where we're interested in the gravitational force on that particle. So mass 1 is our test mass, and mass 2 and mass 3 are the masses that are creating a field at the point where that test mass is placed. And so we can reframe this problem by saying, well, instead of thinking about the gravitational force on a mass, so I can take my two source masses and now think about what's the magnitude and direction of the net gravitational field caused by these two particles at point P, in this case at the origin. Once I know that gravitational field, then I can get the gravitational force acting on mass 1 at that point in space, at the point where I know the field, by using my F equals mg equation. And of course, yes, that's true for mass 1, but once I know the field, that's true for any mass. So take whatever mass you want, place it at that point in space, and you can figure out what the gravitational force is going to be on that mass. So part of what this is hinting at is the fact that you can get the gravitational force on any mass at a point in space as long as you know what the gravitational field is at that point. So how do we learn about gravitational fields? Well, let's start by taking a mass that we'll label big M. And we're going to put it somewhere in space. Then we can take a test mass and place it at some point P. So point P sitting out here, I'm going to place my test mass that I've labeled m0 at point P and now measure the gravitational force that my source mass exerts on the test mass. So part of why we've been talking about a test mass is because that's what we're going to use to probe the gravitational field. So once I've placed my test mass out there in space at point P, I can measure the gravitational force it feels and then use this relationship to tell me what's going on with the gravitational field. Again, this equation says that the gravitational force exerted on my test mass, m0, when placed at a point P in the gravitational field, is given by m0 times the gravitational field at that point. This equation is really what we're going to use to figure out what's going on with the gravitational field. So I can take this equation that tells me how the force and the field relate to each other and solve it for the field. And so what it tells me is that I can basically define the gravitational field as the gravitational force per mass. So what does this equation tell me about how the gravitational force and field relate? Well, the first thing that I can get out of this is the units of G. And again, they've got to have units of force divided by units of mass. So that's newtons per kilogram. But of course, since a newton is a kilogram meters per second squared, if I divide out the kilograms, I'm left with meters per second squared. So part of why we've referred to little g as the gravitational acceleration all semester long is because that's what its units are. The other thing, of course, is that this tells me that the gravitational force and the gravitational field point in the same directions. So I can use a test mass to probe the field. I can calculate out what the gravitational force on my test mass is. I can see what direction the test mass is pulled. And then that's going to let me figure out both the magnitude when I divide out the test mass, the magnitude of the gravitational field, and the direction of the gravitational field at some point P in space, wherever I place my test mass.